Listen, bow, bow, bow. Do you want to know a secret? Bow, bow, bow. Do you want to know how to calculate SNR, signal to noise ratio? A little crazy at the beginning of a nugget is going to help us to remember some formulas, including how to calculate the signal to noise ratio. Let's begin. I'd like you to imagine that our manager once again walks up to us and says, "Hey, is the signal to noise ratio good enough for Bob sitting right here at computer number 2? Because we're considering removing him from the wired network and have him be just a wireless client. We're expecting Bob to use applications such as voice and video that are going to be going over the wireless network, and we want to make sure he has a good experience. So to determine if the signal to noise ratio is quote unquote good enough, we should probably talk about the signal to noise ratio and identify what exactly it is. And that ratio, the signal to noise ratio, or SNR, is the signal that we want to use. For example, let's say currently Bob at his computer has an RSSI. That's the received signal strength indicator. And let's say that RSSI is at currently minus 70. And remember, with RSSI, the closer we can get to minus 0, the better. So for example, minus 0 is not really practical or possible in a real world environment, but a minus 20 would be like amazing. And a minus 50 would be, I guess, okay. And a minus 70 would be maybe iffy, meaning it wouldn't be that great. And as the numbers get bigger, the signal is worse and worse. And again, that's regarding the RSSI. So let's imagine that Bob has an RSSI of minus 70. However, he's still having problems. What could be happening is we could have some interference that's there all the time that's interfering with those same signals. And an interferer on that same frequency could be referred to as a noise floor. And let's say that noise floor, and I'll put that here in green, is minus 95. Green's not that easy to see. Let's go ahead and put it in blue. Minus 95. So that's the noise. So if we wanted to calculate what the signal to noise ratio is, the calculation is the signal that we want to use. And let me put that in black just to be consistent here. So the RSSI is minus 70. And the formula is to subtract the noise floor. So in our case, the noise floor is minus 95. And if you don't know yet, you're going to know now that 2 wrongs do make a right when we're working with math. So minus a negative number is actually adding that number. So our formula would be minus 70, the RSSI, plus the noise floor of 95. And we'll do the math here. I'm going to do 95 minus 70, which gives us 5 here, and a 2 in that column. So the SNR in this scenario, with a noise floor of minus 95 and an RSSI of minus 70, the signal to noise ratio would be 25. And 20 or higher is desirable. And again, the factors involved are going to affect that calculation. So the better our RSSI is and less interference we have is going to give us a higher signal to noise ratio. And what we're shooting for is at least a bare minimum of 20 or higher for our signal to noise ratio. So we've used Insider before, and in the Windows version, this is the Mac flavor of Insider. They have applications for Windows and Mac. And down here we have the crowded 2.4 gigahertz range, and up here we have the less crowded 5 gigahertz range. And currently I have the output sorted by RSSI, the relative signal strength indicator. And this top network of KB is because I'm really close to that access point. And the RSSI is at minus 35, and then I have KB 5 gigahertz, which is at minus 37. This shows me the channels in use, and this is using 802.11 AC. And it's using the channels of 161 and 155, which is an example of channel bonding, using multiple channels. And look at the capable maximum data rate, which is screaming. And then that's right down here. That's this guy. So if you and I wanted to do a calculation for signal to noise ratio, let's go ahead and take the KB network right here. So I'll simply highlight the KB network, and I'm going to freeze the screen just for a moment so I can write on it. Currently it's showing a minus 32 dBm for the RSSI. So I'm going to make a note of that. The RSSI is minus 32 for the KB network. It also shows me right here that I've got 7 other devices that I'm overlapping with, and those are all right here. It's also showing me the strongest overlapping radio, which is this guy right here. So again, the formula for calculating the SNR, just with that one interferer, is the RSSI minus the noise. In this case, I'm going to call that one access point, or that one radio that's competing with me there, as the noise floor, just as an example. And that's going to equal the signal to noise ratio. So the formula would be minus 32, based on this screen right here, minus, and the signal coming in from our next competitor there is minus 67. So it's going to be minus a minus 67 equals, and if I did the math here, that'd be 67 minus 32. So in the ones position, there'd be a 5, and in the tens position, there'd be a 3. So my SNR, at least on these two radios that we're looking at, is going to be 35, which is not bad. Again, we're shooting for 20 as a bare minimum or higher for the signal-to-noise ratio. In this nugget, we've taken a look at how to calculate the signal-to-noise ratio based on the RSSI and the noise that's currently present on that same frequency. I'm glad you joined me for this nugget. I hope this has been informative for you, and I'd like to thank you for viewing.